Okay, the work-energy theorem. This is sort of putting everything together from our previous two sections. Now, when we talked about the jet, we were looking at the amount of work that was necessary to change the kinetic energy of the jet. The jet was taking off from rest, so the kinetic energy initially was zero. So all the work that was being done was really being turned into the final kinetic energy of the system. And we can use this a lot to identify different systems or analyze different systems if we connect how much energy is coming in compared to how much energy we end up with. Okay, conservation of energy. Remember, folks, the energy isn't coming out of nowhere. This energy has to come from someplace. And in the case of the jet, the work that was being done was coming from the combustion of jet fuel with oxygen, and that was releasing the chemical energy to become, of course, mechanical energy, work that was being done. Okay, let's think about this for a few different cases. Again, put away the equations, just think about what's happening and how energy is being transferred. When we strike a nail, okay, our arms are doing work, okay? The chemical energy from our muscles becomes mechanical energy as our muscles contract. We then transfer this energy to the hammer. Now the hammer has kinetic energy. And when the hammer strikes the nail, that kinetic energy is converted into work, and this drives the nail through the fibers and causes the nail, of course, to sink deeper to whatever we're driving it. But also what happens is the energy that the hammer had now disappears or dissipates. It's being transferred from the hammer to the nail. Okay? And of course, work equals force times displacement. What are we doing? We need so much force to drive that nail forward. You can't even push it in with your hands. Okay, we need a tremendous amount of force. So that F is really, really large, even to get a very small displacement. So it's energy transformation. Okay, chemical energies from our muscles become work. Work becomes kinetic energy. Kinetic energy becomes work. Okay, and it's probably dissipated through two different types of energy here. Dissipated as, first of all, heat. Ever hammer a nail and feel how hot it gets? But also it's doing work on the individual fibers, causing the fibers to separate and impaling that nail in that system. Okay, so again, the hammer does work. That work is equal to the change in the kinetic energy, how much energy it started out with, how much energy it ended up with after it hit the nail. Obviously, there's going to be negative work done on the hammer by the nail and positive work done by the hammer on negative work done by the nail on the hammer, positive work done by the hammer on the nail. All right, let's look at a collision analysis. One important thing that is done whenever there's a serious accident is they'll do forensics of the accident itself. I mean, even in the case where, not necessarily it's a fatal accident, but, somebody's seriously hurt or there's a tremendous amount of damage that's being done. And they need to really either assign fault, not necessarily fault to individuals, but fault to perhaps something that went wrong. Maybe it was a failure of equipment, maybe it was a failure of the road itself. But by analyzing these accidents, they can not only try to prevent them in the future, but also improve existing systems. Let's say that we have a driver of a car. They're driving a 1,000 kilogram car, okay? And they're traveling down the interstate with a speed of 35 meters per second. The brakes are applied, producing a net force of 8,000 newtons to slow the car down. So the question here is, at what minimum distance should the brakes be applied to avoid a collision with another vehicle? So what are we asking? We're basically saying, okay, we know that work is going to be done to slow the car down. Work is going to come from the brakes, okay? Work is equal to negative F times, in this case, delta X. It's a work that's going to be done against the motion. We know the car comes in here with some kinetic energy, 1/2 mv squared, okay? All right? So we want to do work on the car to slow it down, to take away this kinetic energy until the kinetic energy is 0, knowing that initially is traveling 35 meters per second, has a mass of 1,000 kilograms, and the work that's done on it, which is negative, is 8,000 newtons. We're looking for how far will it take me to stop? All right, so how do we set this thing up? Once again, we're going to do our work energy theorem, right? The work energy theorem says the net work done on the system from the outside, from whatever, is equal to the change in the kinetic energy, okay? If I bring work in, it's going to speed up. If I take work away, as the brakes are doing in this case, it's going to slow down. Okay. So let's analyze this. What do I have so far? Well, first of all, I want the condition where my final velocity is 0, okay? I want the condition where this term goes away, okay? That's the 0 right down there. The net work done by the brakes, it's right there. Negative F times delta X. That's our equation for work done by friction. And of course, there's no change to our initial kinetic energy. Yes, it's going to change, but we don't really do anything with that term right there. All right. So once again, let's remind everybody what we're doing right here. We're trying to find this delta X right there. So we want that on the left-hand side of the equation. We want everything else on the right-hand side of the equation. Okay, so let's do that. Let us take this term right here, keep it by itself, and just divide both sides by negative Fx. All right, so here we go. Here's our equation. All right. We're going to take this, divide it on both sides. Oops, come on, I selected a pen there. So there we go, that goes down right there. And what we see here is that it doesn't look like a big number, but think about this. It will take 76.6 meters to go from 35 meters per second, okay, to 0 using a force of, how much was our force? There's our force. Using a force of 8,000 newtons, it will take me almost an entire football field, almost an entire soccer field. Okay, soccer is football. Almost an entire football field to stop. Okay, and at 35 meters per second, you're going about 75 miles per hour. This is why it's so dangerous to travel at such a high rate of speed. You really don't have very much room to stop. So again, you can see, simply by conserving energy, we can calculate how much distance I need to produce the work needed to bring the car to rest. Okay. At a given distance of 30 meters, let's say I don't have 76 meters to stop. Let's say I only have 30 meters to stop. How fast will I be traveling if I rear end the car in front of me, okay? Doesn't sound very good because, again, if I need 76 meters to stop and I'm only afforded 30 meters, it doesn't sound like I'm going to change my speed very much. Let's go ahead and do this. Here again is my equation. The net work is equal to the change in kinetic energy. The only work being done, however, is the work due to friction. There's the work due to friction. Here's my delta KE, which is the final minus the initial. Okay? Now it's important to note that this time, this final term, okay, is not going to be zero. That final term is going to help me figure out, well, how fast am I going when I hit the car in front of me? Okay, so let's put everything in here. I put all the terms together. Let me clear this first. Really, we're just taking this equation right here. Okay, the first thing I'm going to do, this whole thing, multiply both sides by 2. Okay, what that'll do is I'll get rid of the 1/2s that are here. All right, makes it a little bit easier to solve. And then I'm trying to solve for the final velocity. So in addition to that, I'll divide everything by m. Okay, so I'm also going to get rid of m here, get rid of m here, and that'll leave m down in the denominator here. Okay, all right, so here's one term, here's a term I want to solve for, and here's the third term. So I'll just rearrange them, okay? Remember, the m's gone, and all we have is VF left. So that's this term right here. Same with this one, and then this one goes over here. Wow, that looks messy. But again, you can do the algebra to show yourself that that does transform to that equation. Now I plug in everything. I plug in my 35 meters per second. I plug in the mass of the vehicle, the friction from the brakes, the distance that I have to stop, 30 meters. Plug them all in, then solve for v squared. I get this right here, and take the square root. Ooh, well, that's not good. 27.3 meters per second is still about 60 miles per hour. So in 30 meters, I've only slowed down from about 75 to 60 miles per hour. I'm going to hit a car in front of me, and I will tell you, getting out of that without injury is going to be highly, highly unlikely. So again, you could see in an accident how much damage is done and actually estimate how fast different vehicles were traveling at the time that an accident took place. Okay, and assign blame. Was a car going too fast? Was a truck going too fast? Was there a condition of the road that made it unsafe to travel at that speed? All this can be done by conservation of energy. And later on, we'll also see that momentum will play a role. Okay, time to do a little aside here. There are basically two types of forces, okay? There are forces we call conservative. I'm going to treat these a little bit differently. In these cases, we say that the work or energy can be recovered, okay? Conservative forces include things like gravity. They include forces like spring forces. They include, other fields, electric fields, magnetic fields. These are all forces that don't depend on the path that you take, but rather depend on more or less your location. Conservative forces, you can always get that energy back. Non-conservative forces generally tend to be dissipative forces or forces where we're adding energy to a system from some other type of energy. So non-conservative. So these two terms come from this. Conservative means that the mechanical energy in the system is preserved during this particular interaction. Whatever mechanical energy you started out with, you're going to end up with. Non-conservative means we've either introduced energy from a different source than mechanical source, okay? Or we've converted some of the mechanical energy into a non-mechanical form, okay? Non-conservative forces would be things like forces from engines, forces from friction. All right. We will treat most conservative forces in the following chapter, in the next chapter, okay? Instead of talking about work done by these conservative forces, we're going to associate these conservative forces with something we call potential energy, okay? But again, that's really the focus of our next chapter, okay? But again, important here, work only depends on the initial and the final position. A conservative force can have a potential energy associated with it. Again, we're going to do that next time. It does not, or I should say the work does not depend on the path of the object. Again, gravity, spring forces, electromagnetic forces can all be turned into potential energy. Non-conservative forces include things like friction, other forms of friction such as air drag, and of course, propulsive forces. Any forces resulting in the conversion into or from mechanical energy of a non-mechanical type, these are going to be considered non-conservative forces. So here's a good example of how non-conservative force works. This is friction. Okay? We have this book being dragged across the table along this path right here, okay, where it goes 3 times as far as it goes right here. Now, as we know, since it's going 3 times the distance and it has the same normal force and same coefficient of friction, we'd expect to lose about 3 times as much energy along this path as along this path, okay? There's a non-conservative force, all right? Depends on the path. And where does the energy go? It goes from mechanical energy into heat as part of the table. All right, let's look at the reentry of the space shuttle. Now, for many years, the space shuttle was really the only human transportation that NASA had. Today, we have replacements for it. We have the Crew Dragon, we have the Orion spacecraft, and we have the Boeing Starliner, plus a few others that are in the works. But in any case, space shuttle was the only way to go, toward and back from the International Space Station. Now, when the space shuttle returned to Earth, basically it had to give up a tremendous amount of energy in the form of kinetic and potential energy. Okay? It had to give up a tremendous amount of mechanical energy. Now, to gain this energy, it's fairly easy to see where that came from. When it went into orbit, very powerful solid rocket boosters were doing work on the shuttle, as well as its own main engines from the energy stored in the external fuel tank. But once you get that energy doesn't just disappear. It has to go someplace. And the way that the shuttle would dissipate all this mechanical energy that it gained in orbit, kinetic energy and the potential energy, okay, was basically by having work done on it by friction. So again, you wanted to land this thing, you had to get the kinetic energy down, so your change in kinetic energy was negative. You get your potential energy down, okay? So your change in potential energy was negative. So the friction as the shuttle entered the atmosphere would cause basically a strong interaction, okay? Actually, the shock wave from reentry would form this very, very hot wall of plasma underneath the shuttle. And essentially, we can understand that this mechanical energy was being converted into heat. And if done properly, almost all the heat was transferred to the atmosphere rather than to the shuttle. Okay, well, that was the idea. So again, if we look at the space shuttle itself, has a tremendous mass, almost 70,000 kilograms. In orbit, it has a speed of 7,800 meters per second, okay? And that corresponds to 2.5 times 10 to the 12 joules of energy, or 2.5, trying to think of, it's mega is 10 to the 6, gig is 10 to the 9, so terajoules, a tremendous amount of energy, terajoules of energy right there that it had to get rid of. Not only that, in orbit, the way that the orbital mechanics work is the amount of potential energy, the amount of kinetic energy are about equal to one another. But you got to be careful with the potential energy, because the potential energy doesn't change as much because you don't really change your altitude as much. But again, 21 trillion joules of energy, at the very least, we've got to get rid of, I should say 25 trillion joules have to be gotten rid of. Okay. And again, potential energy, so 2.5 trillion joules of kinetic energy, 2.7 trillion joules of potential energy. So the friction had to do basically negative 5.2 trillion joules of energy. Just an incredible amount of energy that they had to get rid of. But again, where this energy was going was primarily in the form of heat that would superheat the air. Air, of course, is a gas, but it heated into a plasma state. And the plasma would in turn heat the shuttle, but it would have these protective tiles, which would block too much heat from entering the shuttle itself. Now, unfortunately, in most cases, these heat tiles are fine and they protect the shuttle and keep the plasma from melting any of the components of the shuttle. But on one of the shuttle's journeys, the Columbia space shuttle received a hole in its wing due to falling ice during liftoff, or I should say falling foam. This punched a hole in the carbon-carbon panel on one of the wings, and all of a sudden, this superheated plasma with all this energy was making its way into the wing and basically destroyed the wing, and eventually this led to the destruction of the shuttle. But what's important really to see here is the incredible amount of energy that is associated not only with takeoff, but also with reentry. And during this energy exchange of takeoff and reentry, this is the most dangerous time for any spacecraft. You need so much energy during liftoff to gain the kinetic energy and potential energy needed to reach orbit. And during reentry, all this energy has to be really removed. This is the NASA Orion Crew Module. It's designed to take astronauts to the moon and back. There are similar capsules that are used to take people to the shuttle. I'm sorry, not to the shuttle. The shuttle is retired, to the International Space Station, and those are the Crew Dragon and the Starliner. And the Dream Chaser will be joining us soon. The Soyuz has been doing this for forever. And these use a much simpler technology. Instead of a heat shield placed on an aerodynamic surface that's used to fly, these things are just basically a curved surface, which is much harder to punch holes in. It's actually protected during liftoff, unlike the surfaces of the shuttle. And again, these use these protective tiles, these ceramic tiles, which don't transmit very much heat into the capsule itself. And again, it can safely re-enter. Now, the Orion crew module isn't quite as massive as a shuttle. It's only 9,300 kilograms. So when it re-enters, it needs to get rid of about 1/10 of the amount of energy. That's the kinetic energy right there. So here's the SpaceX Crew Dragon. It's even less massive, and it's traveling a little bit slower. So again, much less energy to get rid of. But on reentry, these spacecraft will have these protective heat shields. The heat shield for this is on the backside of this, that will again hold off the plasma from the hot superheated air from doing damage to the rest of the spacecraft. And again, what you may not realize is with these capsule-like structures, I should use a different color for this. Let me use green. Let me undo this first of all. So use green right here. The capsule stealth, okay, as it's re-entering the atmosphere, isn't really in contact with the plasma directly. If this is done right, there's actually a gap. And it is heated, I believe, radiatively, but the actual bow shock, the actual shock area from coming in, keeps most of the plasma, a small distance away from the rest of the spacecraft. And basically, most of the energy is just lost in the atmosphere. And very little heat will make it to the spacecraft, and those protective tiles are more than sufficient to prevent any damage.